we are going to be working on fn plus 1 minus fn. So for fn plus 1, we are going to replace all the n that is given to us here by n plus 1. So it will be 3 to the power of n plus 1 divided by replacing this n, it is going to be n plus 1 minus fn. This is 3 to the power of n divided by n. And the common denominator will be n plus 1. So for this, I'm going to multiply the numerator by n and the denominator by n, which will give me a n plus 1 in the denominator, which is actually what the question wants us to show later. So this, I will multiply the numerator by n plus 1. So the denominator will also become n plus 1. And now I'm ready to combine them together, which will give me a 3 to the power of n plus 1 and minus 3 to the power of n plus 1. And this is going to be divided by n plus 1. And if you were to look at what you're supposed to show, we are supposed to factorize out 3 to the power of n from the numerator. So what I'm going to do is to break up this into two parts. So 3 to the power of n, 3 to the power of 1, multiply by n, minus 3 to the power of n plus 1. This is going to be divided by n plus 1. And now if I were to factorize out 3 to the power of n, I'll be left with 3n minus n plus 1, which is 3n minus n minus 1. So this is going to be divided by n plus 1, which will give me 3 to the power of n, 2n minus 1 divided by n plus 1. And this is what we are supposed to show. In part 2, we are dealing with the summation of n starting from 1 all the way until n of 3 to the power of n divided by n plus 1, 1 minus 1 over 2n. And in order for us to sum this, what we are going to do is to try to make use of what was proven in the previous part, which means that we want to get this particular expression. But what we are given is this. We need to try to do some manipulations to this expression. And what can we try? We will definitely try to make this into one single fraction first. Because if I were to not try to manipulate and combine this, what else can we do, right? So let's try out with this. Let's try out with this expression. Let's see what is going to happen if I were to make it into one single expression. So it's a little bit of trial and error that we are doing here in terms of algebraic manipulation. So 3 to the power of n, I'm going to leave it as it is. This is a very nice 3 to the power of n here already. n plus 1, I'm also going to be leaving it because there's n plus 1 here. This, I'm going to group it into one single expression. So it is going to be 2n minus 1 divided by 2n. Okay, if I were to group it into one single expression. So we see a 2n minus 1 in the numerator. The denominator is 2n, where n multiplied by n plus 1 is this. So for this 2 over here, I will definitely bring it out of the summation notation. And now within the summation notation, I will have what I've proven in the previous part. So it is to the power 3n divided by n plus 1. And here is a 2n plus 1. Let me extend the line for fraction. So for the denominator, it's going to be n times n plus 1. And this expression here is the same as what we have proven previously, which means that we can replace this expression now in terms of the function f. So in terms of the function f, it is going to be fn plus 1 minus fn. And now we are ready to do a method of difference by expanding this. So expanding this, letting n be equal to 1, we will have a f2. Then minus f1. Then letting n be equal to 2, it is going to be f3 minus away f2. So we see a cancellation here. Let me write down one more row so that I can see a pattern of cancellation. Letting n be equal to 3 gives me f4 minus f3. So we can see this being cancelled. And I'm suspecting that this pattern of cancellation is going to sustain all the way until the last two rows, because two rows is supposed to give me the same pattern. So for the last two rows, I'm going to let n be equal to n minus 1, which is fn minus fn minus 1. Then fn plus 1 minus fn. So we see the same pattern of cancellation, which means that in between here, although we cannot physically write them down, but the pattern suggests that all of them will be removed, which means that I'm going to be left with half multiplied by this fn plus 1 minus f1. And what is fn plus 1? I'm going to replace this n here by n plus 1. So that will be 3 to the power of n plus 1 divided by n plus 1 minus away, replacing n by 1. It is going to be 3 to the power of 1 divided by 1. So my final answer here is going to be equal to half 3 to the power of n plus 1 divided by n plus 1 minus 3. To do part 3, we are going to be heavily making use of the results that we have derived in part 2. So for part 3, we are supposed to do a summation, which is slightly different from what we have experienced in part 2. Let me write it down first. So it is going to be sum 3n, then 2n plus 1. Previously, we had a 2n minus 1 in the numerator. So this divided by n plus 1 and n plus 2. And what I'm going to do is to use the strategy of replacing n by n plus p. It is like the replacing r by r plus p according to what I've discussed on the outline on the Achevas TV. So what I'm going to do now is to replace all the n by n minus 1. Let us see what we are going to be getting. So this n here, I'm going to replace it by n minus 1. And we will replace it by n minus 1 according to the rule that we have discussed on the Achevas TV. In the number at the top here, it is going to be plus 1. So minus 1, here it should be a plus 1. And all the rest of the n will be replaced by n minus 1. So this, it is going to be 3 to the power of n minus 1. Then 2, replacing this n by n minus 1, we have this. And divided by, replacing this n by n minus 1, so we have n minus 1 plus 1. Then n minus 1 plus 2. So moving this one over to the right hand side of the equal sign, we have n starting from 2 all the way until n plus 1. And this is 3 to the power of n, 3 to the power of minus 1. And this is going to be 2n, then minus 2 plus 1, it is going to be minus 1. And I will divide this by, this is going to be n. And here we have an n plus 1. And if I were to bring this 3 out, this is going to be 1/3, right? So 1 over 3, summation of n starting from 2 all the way until n plus 1. And now we have a 3 to the power of n, 2n minus 1 divided by n plus 1. And you probably have noticed that this is actually almost similar to the result that we have gotten from the summation. Sorry, it is almost similar to the summation that we did in the previous part, in part 2, except that it is missing out this 2. It is very easy for us to create this constant 2. What we need to do is to multiply 2 at the outside here so that I can introduce 2 to the denominator. Okay, so this is the addition. And now for this that we have here, at least for the expression that is within the summation notation, we are getting one that is exactly the same as this. It is just that this starts from 1 and ends at n. This starts from 2 and ends at n plus 1. So what I'm going to do is to do a quick manipulation to this. I'm going to once again make use of what we have discussed on the Achevas TV outline. So I'm going to sum from n is equal to 1 all the way until n plus 1. 3 to the power of n, then 2n minus 1 divided by 2n n plus 1. So we're going to be summing this. Then minus away, because we are now starting from 1. But what we were required to do was to sum starting from 2, which means that here we have that one extra term, which is the term when n is equal to 1. So I'm going to let n be equal to 1 for the very first term, to get the very first term of this. Now I'll minus away this so that I can start from 2. So it is going to be 3 to the power of 1, then 2 times 1 minus 1. And this is going to be divided by 2 times 1, 1 plus 1. Okay, so this is equal to 2 over 3. For this that we have here, I'm going to make use of the previous result, replacing all the n by n plus 1. So it is going to be half. Then we have a 3 to the power of n plus 1 plus 1. Let me just write it down. So it is n plus 1, then plus 1. Because I'm replacing this n by n plus 1. So the denominator here is also n plus 1, then plus 1, then minus 3. Okay, so this is going to be the result for this. And I'll minus away the n equal to 1 term so that I can start from 2 all the way until n plus 1. So this is minus 3 over 4. So now we have this. Let me simplify this a little bit further. So I have this. Then here is going to be equal to half. This we have a 3 to the power of n plus 2 divided by n plus 2. Then minus 3. Then minus 3 over 4. I think we are getting really close because 3 to the power of n plus 2 divided by n plus 2 is already appearing. So this, if I were to simplify this even further, this is 2 over 3. Then I'm going to leave the half here, multiply by this, which is 3 to the power of n plus 2 divided by n plus 2. Multiply half to this, combining with this gives me a minus 9 over 4. And finally, if I were to multiply this in, I'm going to be getting, if I were to multiply 2 in, because I'm supposed to get a form that is like this. So I want 3 to be outside here, but I don't want half, okay, because there's no half here. So I'm going to multiply 2 in. So I'm going to leave 1 over 3 outside. Then multiplying 2 in, it will give me a 3 to the power of n plus 1 n plus 2 divided by n plus 2. Then multiplying 2 into this gives me a minus 9 over 2. And I believe we have shown what the question wants us to show. And I'm going to try to code the values of A and B. So from here, matching this to what I'm supposed to show, A should be equal to 1 over 3 and B should be equal to 9 over 2.